Okay, welcome everyone to my continuation of what is algebra. Today, I would like to tell you something about one of the most surprising theorems you see in the theory of groups, in my opinion. Um, it's so surprising because it gives you a classification of something. So the classification of abelian groups, which is ridiculously simple. And in contrast, the classification of all finite groups is just completely hopeless. And so there seems to be nothing in between. That's what makes this statement so amazing. So I say it again, it's just extremely easy. And the proof is actually also pretty easy. So it was kind of known to Gauss, for example. Um, Although Gauss never used the terminology of groups, this was kind of known to him. It dates back, so particularly it dates back a long time. And even up to this day, there's absolutely no hope to classify all finite groups, let's say. And this was came to me at least as a surprise because when you first start looking at groups, well, you have a first class on group theory or whatever. Yeah, kind of all groups are treated at once, and in a lot of examples you see, well, standard examples, whatever, dihedral groups, symmetric groups, and abelian groups. And it seems like they play kind of the same role in the theory, but actually abelian groups from the viewpoint of group theory are completely trivial. And this is what I'm going to explain today. They are basically completely trivial. You can write down all of them, and the result in the end is that all of you know all of them actually. There's basically no abelian group that you haven't seen, up to some fluctuations at infinity. So, but well, for finite groups, there are no infinities, of course. So, yeah, let me just jump right into it. So, the main question you would ask, maybe one of the first questions you would ask is, can you classify groups, right? You learn about groups, there are symmetries, so why not try to classify them? Well, that would be my first question, and actually, I must admit it's a pretty naive question. So there's really no hope. I will show you later. Um, Basically a nice graph illustrating that there's basically no hope to classify these, but let's get already started. So first of all, a big mistake I at least did when I first had a first my when I first learned about groups is, well, you usually study them for a certain small order, whatever groups up to order 9 or something like that. So you only see small groups and you get used to the notion of having groups and so on. Maybe symmetric groups, you know that they grow with n factorial, so they get really big, but otherwise you mostly know small groups. And if you just look at small groups, it looks like basically everything you ever see is abelian. So abelian is, just for you to remember, to recall, if you have AB equals BA, right? It seems to be a priori, well, pretty harmless, innocent looking condition, but it's an extremely strong condition. And that's basically what I'm going to tell you today. But anyway, so let's look at groups of order up to 9, first of all. And I have marked in red where there are non-abelian groups. So up to order 9, there are only non-abelian groups of order 6 or 8. Otherwise, you always have abelian groups, and that's, well, how to read it. So here's my all, what is it, a column. Here's my abelian column, just the number of them, and the ratio of abelian over all, right? So if you just have one group, well, so this group is a trivial group, of course, and the trivial group is of course abelian, then, well, the ratio is 1. And you go on, and here, for example, for 6, you have the symmetric group S3, and you have Z mod 6. So you have two of them, and symmetric group is not abelian, Z mod 6 is abelian, so the ratio is basically 1 over 2. For order 8, you have a few more groups. I will come back to that in a second, but still the ratio of abelian groups is pretty good. It's roughly 0.6. And, well, that's what you first see in a class on group theory. You see low order groups. And at least I got very fooled by low order groups, because I thought, oh, well, most groups are abelian. I mean, most groups. And up to order 9, basically all groups are abelian. If you look down the line much further, it turns out that this is just, it is just so wrong. It's just so ridiculously wrong. So for example, the groups of order, what is it, 265. So 265 is the power of 2. Just a fun fact. But anyway, for a power of 2, you always have a huge number of groups. So in this case, you have whatever, 50, let's say 50,000 groups. And only 22 of them are abelian, actually. So almost all groups in this case are not abelian. The ratio is pretty small, of course. It's 22 over this 50,000 thing. So the ratio is super small. And we are just at 256. So if you go a lot further down and you hit this power of 2, it's also a power of 2, then actually it's not known, at least in 2021. The number of all groups is not known. The number of abelian groups is extremely easy to calculate. It's small, well, reasonably small, 56. So the number of all groups is not known. It's probably ridiculously huge. So this ratio, also strictly speaking, it's not known, is ridiculously small, right? So this is kind of this small number bias that you see here. For small numbers, it looks like almost all groups are abelian. For big numbers, nah, no way. Almost all groups are not abelian, actually. So in some sense, classifying, let's say, all finite groups seems to be a little bit aiming too high, but maybe you have a chance of classify abelian groups because there don't seem to be so many of them. And it turns out that you can actually easily classify them, and the statement is pretty nice. So let's just have a look. Okay, keep in mind, all groups kind of out of reach, abelian groups, that's what we're going to try. Okay, and it turns out that's why it was known to Gauss, basically. All you need to classify, a little bit stressing right now, all, right? But anyway, basically what you need to classify finite simple groups, finite abelian groups is a Chinese remainder theorem. Um, and this is a really classical theorem in mathematics. I will recall it in a second, but it really kind of the first appearance is the third century in a Chinese math book, and it's sometimes contributed to this Chinese person whose name I don't dare to pronounce. Well, I do dare to pronounce it. I give it a shot. It's probably wrong. Jun Tzu. Okay. Anyway, it's it's more than 1,000 years ago. It's way more than 1,000 years ago. And it has a very well-known solution. And basically, what you do is, and this is the English translation from this original Chinese book that I found on Wikipedia, linked below. It's kind of a fun history. Is the following. So this person or this book asks, there are certain things whose numbers is unknown. Okay, so you want to know a number. I call it n. Okay, my n. So what is n? Basically, that's the question. And they don't want to tell you what n is. They give you a riddle. And they say, okay, if we count by threes, which in modern language just means if you divide by three, so you arrange everything as multiples of three, we have two left over. Right? That's just saying n is congruent to mod 3. Okay, so this is this one. And then they tell you a little bit more. By fives, so if you arrange by fives, then we have a leftover of 3. So this is this one. And they also tell you a little bit about the 7. So if you arrange them by 7, then you have a leftover of 2. And basically, they want to solve. They want you to solve this system of equations. The only thing that might look a little bit unfamiliar, so you definitely by now know a system of equations, might look a little bit unfamiliar here is that it's a system of congruences. So equations modulo p, basically, modulo prime. And I leave it to you to solve this puzzle. It's a 1,000, what is it, 1,700-year-old puzzle, roughly. And it's not so hard to solve. But anyway, so the theorem itself is kind of that you always have a unique solution. There's only one solution in a certain range, and that's the unique solution of the system. And certainly you want to restrict to this range because as soon as you go over this range, kind of the solution will itself repeat. But anyway, in this range, there's only one solution. And the only thing, this is a really good theorem, like it The proof actually is also effective, so it tells you a way how to find this solution. And nowadays you can ask any computer algebra program, of course, to do it. But anyway, you need to be a bit careful, and that will be important for my classification, because the things you arrange it by, so if we count them by threes, if we count by fives, if we count by sevens, so those three things, they should be co-prime for really this theorem to apply. So if you have something like a 2 and 8, so if you would arrange things by 2s or 8s, then you get more solutions. And we will see actually why that happens in a second. But this is kind of the classical Chinese remainder theorem. So you kind of have a unique solution, um, or a reasonably unique solution, if you restrict to things that are co-prime. Very classical, just solving system of congruences instead of something that is very familiar to you. Instead of solving system of linear equations, you solve system of congruences, and you still have a really reasonably nice answer. That's a Chinese remainder theorem. Okay, and then it start thinking about abelian groups, and it turns out that you don't need to know more than basically the Chinese remainder theorem to classify abelian groups. You need to know a little bit more, of course, to make it precise, but not too much. And it turns out by Chinese remainder that there are basically only two abelian groups. One that I'm going to ignore up to the next slide, namely the infinite one, the integers. Of course, that's an abelian group. Um, and all the other abelian groups are kind of z mod p to the k for k being a prime. Okay, so for instance, z mod 4, which is 2 squared, of course, for z mod 2 squared, right, for example. And why is that? Well, let's just go through the list. Okay, for this order 1, order 2, order 3, and so on. So for order 1, there's only z mod 1. That's not really hard to see. For order 2, there's only z mod 2. That's not hard to say. For order 3, there's only z mod 3. That's also not hard to see. And then you come to order 4. Order 4 is the first funny one. So order 4, you have z mod 4, obviously. So for if that isn't clear, by the way, I just stress it. For each order, you definitely have at least one group, which is z mod n, where n is the order. So z mod 4 kind of comes for free, z mod 6 comes for free, z mod 8 comes for free, and all of these come for free anyway. The point is there are no others. And the reason is that for z mod 4, Chinese remainder fails. So z mod 4 definitely has an element of order 4, which is 1, while z mod 2 cross z mod 2 has no element of order. So this is generated by those two elements. It has just no element of order 4. So they can't be isomorphic. So in this case, you would count two different ones. For 6, something funny happens. For 6, you can actually use the Chinese remainder theorem to see that 6 is isomorphic to 2 cross 3. Why? Well, because this element now, the 1, 1 element here is now of order 6. Why is that? Well, if you add it to itself, for example, I'm writing abelian groups additively, by the way, then you would get this one, right? This is just adding it twice. But it's still not there. You can go on, you add another copy of this, and you're still not there, and so on. And you will realize after 6 steps, you come back to where you started. And this is basically because of the Chinese remainder theorem. The Chinese remainder theorem would tell you that basically what you're trying to do here is to solve a system of linear congruences, and there's a unique solution that you can pick out. That's the Chinese remainder theorem. For a prime power like 8, this is the last one, 8, there's just, again, no Chinese remainder theorem. So basically what you need to do is you need to list all possible ways of factoring the number 8. So z mod 8 can't be isomorphic to z mod 4 cross z mod 2 because z mod 8 has an element of order 8. And z mod 4 cross z mod 2 just doesn't have any element of order 8. You can't play the trick I just played for z mod 6. It just doesn't work by Chinese remainder. Similarly, the middle one has an element of order 4, but the right one here certainly doesn't have any element of order 4. So this really looks like you can just list all the finite simple groups by looking at the factors by Chinese remainder. And this is essentially the theorem, right? So you can classify all finite abelian groups. And even a bit more, you can classify all finitely generated abelian groups. Okay, so things you can't classify, for example, is Q, uh, which are things that are too big. So if your infinity goes too big, you see very strange patterns. But don't worry about it too much. So in the finitely generated case, and this just means you have a finite number of generators. In particular, this is true for any finite group. This is again a condition to really just to avoid things like Q. There's really a unique decomposition. Oh, well, there exists a unique decomposition, and it's exactly what I just did here. So you have your group, you start with it, and you split it into, well, it might be infinite, so you have a certain number of copies of Z. But let's focus on the finite part. So all the finite parts are a certain number of Z mod Qs, and all Qs are prime powers. Right? So exactly like I did here, right? So Z mod 8, 8 is a prime power. Z mod 4 cross Z mod 2, 4 and 2 are prime powers. Z mod 2 cross Z mod 2 cross Z mod 2. And yeah, before I show you that in action using Mathematica, let me just stress what's going on here. So you can really classify all those finitely abelian groups. They're just given by a pair or by a tuple of a number, which is a rank, and a certain number of prime powers, and that's it. It's just a pretty simple statement, right? Any finite abelian group. So for finite abelian groups, you can ignore the rank here. Any finite abelian group is just determined by a certain finite collection of prime powers. That's it. And that's of course then really easy because for a given number, the counting problem is basically trivial, right? You just have to do exactly what I did here. You just have to count the ways to arrange prime powers. Let me show you that actually in action. So here we are, Mathematica, linked in the description. And what I can do here is I can well, this is my order of the group. I can just pull the slider here, and the theorem basically says the following. It's ridiculously simple, I said. It looks like there's no hope to classify abelian groups, at least for me, just naively, but it's really, really simple. So for example, if you would wonder how many abelian groups are there of order 147, so 174, 47. So we can also do 174. 174. 174 is easy because 174 is actually 2 times 3 times 29. So Chinese remainder tells you that this is 2 times 3 times 29. And there's no way, well, you can reorder them, but that's boring. But otherwise, there's no way to do anything. So you have exactly one abelian group of this order. Very easy. So let's go back to 147. 147 is 3 times 7 squared. So what you need to do is, well, you need to look at all ways to arrange squares of primes, prime powers. So 3 just comes with power 1, so it just is what it is. And you have two choices for 7. You can either say it's 7 squared, so it's 49, or you can say it's 7 cross 7. So you get just two options. And this is just extremely easy. And of course, at prime powers, like 128, you just have many options because 128 is 2 to the 7. You need to just write down all ways to arrange 2 to the 7, well, in different ways, like 128 or 64 times 2 or 32 times 4 or 32 times 2 times 2, something like that, right? Let me give you one more. So this one is a really bad one. It's 2 to the 6 times 3, and the 3 is pretty easy. You just write it down. It just is what it is, and you just write down all ways to split basically 2 to the 6. And if you're wondering, so let's find a prime number, something like 17. 17 is probably the biggest prime number I know. Of course, for a prime number, this is really easy. You just have exactly one way. Right, so let's do this one, 200, 5 squared and 2 cubed. So you can split 5 either in 25 or 5 times 5. And you can split 2 in 8, the one I showed you, right? In 8 for 2 or in 2 to 2. And just collect all possibilities. Yeah, and that's the fundamental theorem of, it's also sometimes called the fundamental theorem of abelian groups. basically the classification of abelian groups, up to fluctuations at infinity. And I personally think this is very surprising. Again, I say it again, from two perspectives. First of all, you can classify abelian groups. And second, the statement is pretty simple. I just basically showed you how it works, right? You just arrange prime powers. And in contrast, in really stark contrast, classification of non-abelian groups is kind of hopeless. So here I've plotted the ratio of non-abelian groups versus abelian groups. So ratio 1 means any group you find of that order is abelian. So the order goes in this direction, and the ratio goes in this direction, right? So you start off, that's what I showed you before here, right? You start off by thinking almost all groups are abelian, and you can see it here. But actually most of them are not. So here, for example, at 64, which is a power of 2, you basically have no abelian groups at all, right? The ratio is basically 0. So here's 0.2, the ratio is basically 0. And as you go along, so this is a slice 0 to 100. And this is a slice, what is it, 2000 to 2100. As you go along, you will see basically no groups are abelian. So it's very surprising that you can actually classify abelian groups, because the analog problem for just finite groups is just no, it's not going to happen. Anyway, I hope you enjoyed the video. So classification of finite abelian groups is ridiculously simple. It's basically a matter of arranging prime powers, and it builds on well, old Chinese mathematics, if you want. So it's kind of well known for ages, also usually not stated as such. Yes, so I hope you enjoyed the video, and I hope to see you next time.